Hi, my name is Christian Chin, and this will be my Lab 2 Motion of a Falling Object lab report. The primary purpose of this lab is to observe the motion of an object when velocity and momentum are changing, meaning the net force on the object is not equal to zero. We will apply Newton's second law, the momentum principle, and consider the effects of gravity on an object versus the gravity and drag force on an object. I chose to record a dry eraser dropping along a meter stick in the physics lab room. The eraser will drop for 0.3 seconds, or 9 frames, starting from 0 meters and ending up at negative 0.834 meters. Due to weight force, the net force is not equal to 0, thus momentum is not constant and velocity is not constant. In this case, I calculated initial velocity to be negative 1.928 meters per second using the average velocity formula, since the object is not at rest at the initial position of the experiment. Opening up the first program, I set the ball's mass to be 0.034 kilograms and the ball's velocity vector to have a y component of negative 1.928, which I calculated through data in Tracker. To simulate the velocity and position of the object, we must again change the velocity and position equations to model the velocity update and position update formulas. Thus, I have changed the second part to both of these coded equations, adding F net divided by ball mass multiplied by delta t to the velocity equation, and ball velocity multiplied by delta t to the position equation. We will use the weight force formula in this program, setting g equal to 9.8, since it is the gravity on Earth, b equal to 0 since we are not accounting for drag force yet, and j hat equal to 0, 1, 0, the unit vector for direction. Weight force is set to equal net force since it is the only force acting on the object right now. Opening up the second program, I have set the proportionality constant equal to 0.0214 through continuous testing. Furthermore, I have added a drag force constant which is set to negative b multiplied by the magnitude of v squared multiplied by the normal velocity vector, which describes its motion. I have modeled the arrows based on drag force and weight force, setting the arrow scale equal to 6 meters, calculated by dividing 2 meters by the magnitude of the weight force. The velocity of an object in both programs are decreasing, but the program that included drag force has the object's acceleration decreasing over time, while the first program's acceleration was constant. Thus, in the second program, as the object continues to speed up, the magnitude of the drag force becomes greater, decreasing acceleration. All three graphs have positions that decrease with time in a nonlinear fashion. However, the object's final position in the program that only accounted for weight force is negative 1 meter, while the object's final position in the program that accounted for both weight and drag force is negative 0.8 meters, which mirrors the experimental final position. Due to the high accuracy in position, velocity, and acceleration between the experimental graph and the graph with both forces, we can conclude that accounting for weight and drag force attributes to a good prediction in motion. I recognize that there have been some possible sources of error as I completed this lab. The first error may have been analyzing the captured video through Tracker inaccurately, since it is difficult to visually pinpoint the center of the object at each frame. The second error may have occurred if the camera that captured the object in motion may have not been completely parallel to the object's motion, producing a slightly inclined camera angle and leading to slight video distortion. Examining the velocity in both models, I can conclude that neither model predicts terminal velocity, since neither model reaches a constant velocity, although the model with drag force comes close. If the model was given more time, it may have reached terminal velocity. If an object was thrown downward, its terminal velocity would stay the same since the object's mass does not change. With a large initial velocity, the object would reach terminal velocity faster. By incorporating the principles of weight force and drag force along with Newton's second law, we can determine the accurate motion of an object moving in a downward direction. As the speed of an object increases, the magnitude of its drag force also increases, decreasing the acceleration of the object. Thank you for listening to my report. I hope you have a great day or night.